Hello everyone. This is a brief description of a prototype that we have developed for the final project of course EE533 Network Processor Design and Programming. We are Team Deadpool from the University of Southern California and our project is Firewall using deep packet inspection. Moving on to motivation. In today's world of internet, data security is a vital necessity and a significant cause of concern. We recently have heard about the data breach at Equifax, due to which sensitive information of around 143 million US consumer was compromised. This has resulted in nearly $80 million lost to the company. As recent as March 2018, Frost Bank admitted that it was victim to data breach, due to which sensitive data like signatures, account balances, and check were compromised. Such intrusive attacks are increasing in the degree of success and are predicted to increase in number in coming years. This shows that the existing systems are not robust and are resilient enough to cope with the increasing competencies of the hacker. Our prototype is an effort to mitigate this problem. Our design is a network-based intrusion detection system that identifies the presence of known signatures by performing deep packet inspection. So I'll try to explain the project to you by means of an analogy. This is Bob, and Bob is a security manager at airport. So scenario 1, where there is no security check, everyone is able to board flight. The guy you see with briefcase is carrying explosive with him and he is still able to board the flight, which unfortunately leads to explosion in the aircraft. We have a scenario 2. Now Bobs decide to manually check every passenger. As you can see, the process is slow and it's getting crowded. The Bob is able to check everyone manually and find suspicious people. The entire process is slow and everyone is getting restless. We have a scenario 3 where Bob has installed the new metal scanner. As you can see, the process is fast. Bob is able to check everyone and can easily catch people carrying suspicious objects with them. Now let us try to correlate our analogy with the computer network hardware. The travelers are analogous to the packet coming in the network. People carrying suspicious objects are analogous to packet having malicious content. Let's correlate the scenarios. The first scenario, where people could easily board aircraft without any security check, which led to explosion in aircraft. Now this is analogous to having a network having no security check. An explosion is analogous to breach of network. In the second scenario, we had Bob manually checking every passenger. We saw the line was getting crowded. Now this scenario is analogous to having a software-based firewall which checks packet for malicious content and drops such packets. But this process is slow, the latency is high, and the throughput is low. In the third scenario, we had a metal scanner to do the security screening. And we saw the process was fast, then scenario 2. Now this is our design of a hardware accelerated firewall using deep packet inspection. The latency of the system is low, the throughput is high, and we are able to achieve functionality on a gigabit Ethernet link.
This is the 7-layer OSI model. As you can see, since the software is running on the receiving node, the packet has to go through all the 7 layers of the model, and the malicious packets get dropped at the application layer. While in the hardware implementation, the pattern checking is offloaded to the router, reducing the CPU utilization of the receiving node significantly. Packets only need to go through 3 layers, and malicious packets get dropped at the network layer, which reduces the latency. In our hardware, we implemented a dual-core 4-threaded RISC-V processor. Our processor is a 5-stage pipeline processor, which uses a 512 location instruction memory. We're also using 4 program counters, 1 for each thread. The thread gets selected by the thread scheduler logic. We have a 64-bit wide, 256 location deep, convertible SRAM/FIFO in the memory stage. Our processor supports arithmetic logical instructions in addition to load, store, and branch instructions a total of 28 instructions are supported. The two cores in our design are connected serially and working independently with 4 threads of each core operating on the same packets. The serial architecture pipelines the workflow and increases the throughput. As the packet arrives at the FIFO 0, core 0 reads a copy of the packets into the register file, and let's see what the core 0 does. So the core 0 reads the third flit of the packets from the FIFO 0, which is the protocol field in the IP header, and checks what protocol the packet is encapsulated. If it is a TCP packet, core 0 would tell the FIFO to drop the packet. As you can see, the packet is getting dropped. Otherwise, the packet is sent to the core 1 and the hardware accelerator, and the next packet comes into the FIFO 0 at the same time. Core 1 and hardware accelerators are responsible for pattern matching, and all the possible byte alignments are checked. Let's see what the hardware accelerator is doing. The hardware accelerator has a word match module which compares a 7-byte long signature against the content of the packet. The signature is matched against all the byte alignments. If at least one match is detected, the match signal is generated and the packet is dropped. So as you can see, the packet is dropped if the match is detected.
Hello everyone, this is a short demonstration of our hardware implementation working in real time. To demonstrate that we can detect and drop transport protocols, we are blocking TCP packets. To demonstrate that we can detect and block patterns inside the packets, we are blocking patterns corresponding to websites like BBC, Build and CNET as an example. So going forward with the demonstration, I would like to first show that TCP packets can be dropped with our design, and also that the packets with the patterns can be dropped after the first one. So going ahead, I would like to first dump the bit file onto the NetFPGA. And once that's done, I'll have to do RKD on the NetFPGA. Yeah, that's also done. Now I have to set some software registers on the NetFPGA. Here I'm setting the patterns 1, 2, 3 in the NetFPGA so that the NetFPGA can check for these patterns in the packets that are going through them, and essentially drop these whenever required. I'm going to check the matches hardware register to make sure that all of them are zeros, and now I'm going to set the software register which is corresponding to tell the NetFPGA to drop the TCP packet or UDP packet depending upon the input that we give. Here if I'm giving UDP, then it's going to drop UDP. I've set it to UDP to just show that the TCP packets can also be sent through the NetFPGA, and UDP packets can also be dropped in the NetFPGA and vice versa. So let's just go ahead and send a TCP packet from server which should be running on node 0, and the client which should be running on node 1. And before that, let's just cross check whether the whole system is pinging or not. Yeah, it's indeed pinging, and let's do the same from node 1. Yeah, everything is working. So let's just send the TCP packet. I'm going to set the TCP server on node 0. Now I'm sending the TCP packet from node 1, and since we have received the acknowledgement from the server, this means that the TCP packet has been sent. Now let's set the software register which is corresponding to UDP or TCP to TCP to just show that the TCP packet can be dropped. Now let's just ping again. to just make sure. Yes, it is pinging, and it is also pinging. So now let's send the same packet from node 1 to node 0, and let's see what's going to happen. Yeah, as you can see, there's no acknowledgement that is being received from the server. This means that the packet has been dropped. Now let's just send the UDP packet from node 1 to node 0 and see that the packet is indeed not dropped. For that to happen, first we have to set a UDP server. And similarly, we have to set a UDP client and send the same packet. Now you can see that the UDP packet has been received and without any kind of packet drops, and this essentially says that the system works perfectly fine. Now let's go ahead and look for the patterns inside the packets and drop the packets which have the patterns. For that to happen, I am sending a different packet, different file which has patterns in them, and essentially see that the packets are being dropped. So for that to happen, I'm going to use this particular command on node 1 to send the packets to node 0, and here we can see that 3 packets are dropped, and this says that the pattern matching and dropping of the packets with the patterns is also working perfectly fine. And we can cross check this with the matches hardware registers which is present on the NetFPGA. So here we can see that 2 patterns have actually been seen, and essentially the packets are dropped. SNOT is an open source network based intrusion detection system which has the ability to perform real-time traffic analysis and packet logging on internet protocol networks. The rules in SNOT are written to detect 21 protocols and configurations, and the rule files are written accordingly. I am going to run the protocol detection using SNOT on node 0 first, and then run the protocol detection and dropping using combination of our hardware and SNOT. Please bear in mind that our hardware is implemented on NetFPGA. Firstly, I would just like to show you this snot.conf file. Here the home net is node 0 and external net are every other node apart from node 0, and this local.rules is the file which contains all the rules which we want to detect. And let's come out of this, and I would also like to show you the local.rules file. Here are all the rules that we are going to look for, or the patterns that we want to look for in the packets, and coming out of this as well. Now let's just test the snot.conf file by using this particular command. Yeah, here we can see that SNOT successfully validated, and now I would like to show you that 21 SNOT rules are red and 21 detection rules are red. So this says that the rules are valid and the configuration has been successfully done. Now let us run SNOT in IDS mode, and after that is done, let us just send a packet from node 1 to node 0 and see what happens. So making the SNOT run in IDS mode. While this is running, let us set up the TCP. Let us set up the servers, UDP server in node 0 and UDP client in node 1, but before that let's first dump our bit file onto the control node. So for that, let's just dump it. So as you can see, I'm just first dumping the reference router bit file so that I can later compare reference router's performance with our bit file's performance. So after this, I'm going to dump RKD. Yeah, now let's just make sure that the whole system is able to ping. Yes, and let's ping node 0 from node 1. Yeah, so everything is pinging. Now let's go ahead and send 80 packets from node 1 to node 0 and see how many patterns are actually detected. And before doing that, let's run snort on node 0 again. And now while that is running in the background, let's send a UDP packet from node 1 to node 0. Okay, let's set up node 0 as our yes. So UDP server has been set and it's listening on 5001, and let's send a packet of UDP from node 1 to node 0. And let's also make sure that yeah, the snort is still running. And now let's send the packet from node 1 to node 0. Yeah, now we have sent the whole packet, and you can notice that 0 packets are dropped, and that's a good news. And let us just look into the results that are presented by snort and see how many patterns are actually detected. Here all the 21 patterns are detected, and you can also see that there are SIDs 49, 1,049, 1,053 and 1,052 are also present here. Actually, these SIDs correspond to patterns of BBC, build and CNET. So since we are running reference router on the net FPGA, we are getting these packets. Otherwise, if our router design or our bit file was dumped on the net FPGA, these packets would have been dropped, since our hardware essentially drops BBC, CNET and build packets. So let's just cross verify that by dumping our bit file on the net FPGA and again running snort on node 0. So for doing that, let's just dump the bit file. Yeah, the bit file is, yeah, it's dumped. And let's set up the software registers as we have done earlier, and the same patterns. And now let's check the matches. Yeah, nothing matches. Now let us set this to TCP. Let's also do RKD. Now let us see if it's pinging. Yes, it's pinging. So let's go ahead and send a packet from node 1 to node 0. Since the server node 0 is already listening as a server, which you can see here. Let's go ahead and send a packet from node 1, and let's essentially send 80 packets using this command, and let's see what's going to happen. And here straight away we can see that 3 packets are dropped, and more elaborate description will be provided by Snot. Now since I've shown you that the packets are dropped, let's see the details of what packets are dropped in Snot. But for that to happen, we have to run Snot in the background, and we can do that by setting this. Yeah, now let's send, since N0 is listening, let's go to node 1 and essentially send the packets. Yes, so again we can see that 3 packets have been dropped, but now we can see that these little patterns have actually been seen. And the good news is, as I told you, the patterns which are hard-coded in our hardware are 49, 52, 52 and 50, and which are actually present in the previous iteration of Snot. And now we can see that 49, 50 and 52 are actually not present in this in this process, or in this Snot, in this running of Snot. This means that our hardware in NetFPGA is actually blocking these packets, or the patterns, or the packets with these patterns. Let's next go ahead and do the same for 150 packets and 250 packets, and see how the microseconds, or the time which these patterns take, get affected. So for that, let's just go to node 1 and do the same process again, but this time let's just take up this. Yeah, and again we have 3 packets which are dropped, and now let's do go to control node and basically go to node 0 and set up the Snot this time. I'm doing this so that we can get the details of what are the packets that are dropped. Now go to node 1 and now we can see that, yeah, you can see that again the patterns of 49, 50 and 52 are not seen. That means that the router, the bit file that we've dumped on the NetFPGA is working exactly the way that we wanted, and it's dropping the patterns of build, CNN, build, CNET and BBC. But here we can observe that the time taken by these patterns has increased very well, and this means that as the number of packets increase, the time taken by each and every pattern or each and every rule will increase. And we'll observe this once again by sending even more number of packets, and this can be done. First let's make node 0 run Snot in the background, and node 1 send the packet. This time let's send 250 packets. Now let's see the details. Here again we can see that 52, 49 and 50 are not present. That's a good news. And again, the time taken has actually increased. And yeah, that is for this not that is how we came up with the software benchmarking. Different hardware and software benchmarks that we considered are latency with increasing number of packets, throughput with increasing number of packets, and latency with increasing number of patterns. From this plot, we see that as the number of packets increase, pure software implementation incurs huge latencies, while our software hardware implementation performs decently. From this plot of throughput, the software implementation's throughput plateaus while the number of packets increased, but our implementation shows promising improvement. From this plot, we can interpret that the software takes increasing amount of time with increasing number of patterns, while our implementation takes almost the same time for increasing amount of number of patterns. So this is a project timeline. And in conclusion, we see that our implementation outperforms the pure software implementation in all the benchmark results, and hence a better implementation. Thank you.